Welcome back, Science 10. Today we're going to be talking about mechanical energy. So we're going to take our concepts of kinetic energy and gravitational potential energy that we've been calculating, and we're going to combine it into one fun time. So let's get started. So mechanical energy, sometimes we have two sources of energy that combine to do work. Okay, mechanical energy is used to apply a force to another object and do work. Okay, so what we're taking here is we're taking two different types of energy and performing work. So we have mechanical energy is just the sum of kinetic energy and potential energy. So to view this, I think it's best we head back to our little skate park. Okay, so if we just go into the basic one like we looked before, we'll do the bar graph again. Okay, speed, why not? Okay, so if we're going to take a look at what we got going on here, let's go in slow motion so it's a little easier to understand. This time when we come up here, okay, we have a total energy on the far right side of this bar graph. Okay, that is the total energy of our system. Now, what do you notice happens as we move further and further down the ramp? You can see our potential energy, which was the highest at the highest point, is now turning into kinetic energy as we're going through until we reach the bottom point, where we have no potential energy, and it's all kinetic energy. Now, what do you think is going to happen when we go back up? That's right, we're going to see the potential energy increase now, and the green bar of the kinetic energy decrease. Okay, so as you can see, going all the way back down, okay, we see kinetic energy increase to its maximum, and then, okay, we'll go back up to the top where it's potential. But at a point anywhere in between the lowest point and the highest point, we see a combination of kinetic and potential energy, like we see on the side here. Okay, that is what we call mechanical energy. So at the highest point, when he's up here, he has potential energy. When he's down here, we have kinetic energy. Here, we have both kinetic and potential. Okay? So let's head back to our presentation. So we can also take a look at a demolition ball taking down a building. Initially, like a pendulum, okay, we see that the thing starts with potential energy. As it gets to that highest point and it swings down, we see it convert into kinetic energy, which then converts into work and smashes the building apart. Okay, so that is what we end up seeing, that overall conversion. This is what we would consider to be mechanical energy because it contains both components of potential and kinetic. Okay? So, again, it does work upon the structure. A nice little example is skiing. Everybody loves skiing. Okay, if we have a skier at the top of the hill, as we can see, we have 50,000 joules of potential energy. As we progress down the hill, and this is, again, relative to the ground. Okay, as we progress down the hill, the kinetic energy increases and the potential energy decreases. Because, again, we see our skier starting to move faster until it reaches this bottom point here. We still have a little bit of potential energy relative to the ground, but we see a good chunk of it turned into our kinetic energy. Okay? Hopefully it's enough kinetic energy to get some wicked air. We see that he comes flying off the jump at this height now. Okay? And again, we see a combination of kinetic and potential energy, which is mechanical energy. Okay? So again, when we add these two components up, our total is 50,000 joules. Which is what we started with at the very beginning. Okay, so again, all of these totals should add up to 50,000 because we're assuming in this little diagram that no energy is lost. Okay, this is what we're assuming. Okay? So again, as we reach down this point, we land, we have no potential energy, and we have all kinetic energy. Okay? So again, mechanical energy is just a combination of the two. So problems we often encounter are in terms of pendulums. Okay? Pendulums are a great example, like we mentioned with the wrecking ball before. Okay? With a pendulum, as you see on a clock, it goes back and forth. Okay? So at point A, we have potential energy, but no kinetic energy. Okay, so we see no motion when it reaches this point for a brief second. As it swings this way, like the diagram mentions, we see kinetic energy increase and potential energy decrease. Okay, and again, until we hit this point here, at point D, where we have all kinetic energy. So we have a large amount of kinetic energy, and we have no potential energy. Okay, until we start moving back up. Okay, when we move back up, we see kinetic energy decrease and potential energy increase. And again, it continues to go back and forth, back and forth. Okay, so again, we see the combination of both. So in between point A and point D, we would see a combination of the two, which we would call mechanical energy. Same thing on this side over here. Between G and D, we would see mechanical energy in between there, as it's progressing up to those maximum and minimums. Okay, so let's take a look at an example. So an example, 30-gram baseball is thrown with a horizontal speed of 5.00 meters per second. The total mechanical energy of the ball is 0.750 joules. Calculate the gravitational potential energy of the ball. So let's write down what's important. We see a gram unit here, which is usually a good indicator of a mass. Okay, we also see the speed of 5.00 meters per second. Okay, and we also see mechanical energy of 0.750. So we'll just go EM is equal to 0.750 joules. Okay, so we know with a baseball getting thrown, okay, if we look at a pitcher's mound and home plate, okay, when a ball's being thrown, okay, we end up seeing that, again, it should have some potential energy. It should also have, okay, it should also have some kinetic energy as well, which we can tell if it's moving, right? We know it's got a horizontal speed. So we know we're going to need to find EK, or we're going to need to find EG. Because we're looking for the gravitational potential energy of the ball. So this is the guy we're looking for. Since we have mass and velocity, we can calculate our kinetic energy. So that's where we're going to start. Kinetic energy is equal to 1/2 mv squared. Plug in everything. 1/2 is equal to, sorry, we're going to have to back up a step. Convert this into kilograms. We divide by 1,000. So we get 0.030 kilograms. Okay, so we'd see 0.0300 kilograms times our speed of 5.00 meters per second, all squared up. Okay, so now what we get for an answer here, it'll take a few seconds to calculate it, and we get an answer of 0.375 joules. Okay? Now, we found out the kinetic energy of the ball. Now we're looking for the gravitational, but we're given the mechanical energy. Okay, so we know, because it's going to move down the page here, our mechanical energy is equal to the kinetic energy plus EG. So to rearrange this and move this guy over here, we need to subtract. So we see EM minus our kinetic energy is equal to our potential energy. Okay, so when we're dealing with this here, we have, now it's just an easy plug in and solve. We have our mechanical energy, we have our kinetic energy. Well, let's finish up the problem. 0.750 joules minus 0.375 joules gives us our potential energy. Okay, so our potential energy here, in this case, is going to work out to 0.375 joules. Okay, so that's our final answer. So again, it's just using the concept that, again, this baseball, like my crummy diagram at the top says, has both kinetic and potential energy. So we can use that information to find one of them in particular. Okay, so again, good practice. So I want you to take a few seconds and write down 4 or 5 important points about the presentation and bring them into class tomorrow. We're going to be doing a lot more practice tomorrow, so make sure you're familiar with kinetic and potential energy and how it plays into mechanical energy. Thanks for listening. I'll talk to you tomorrow.